So with this, let us actually start solving the mathematical expressions that we had written out over here. So we've got these two generic equations, and using this we will write down the mathematical equation. So nothing is known. This is unknown. This is unknown. The probabilities are known. The rewards are known. Gamma is known. Utilities are unknown. So in all, we will have n equations like this, one for every s. And I need to say that you will not get it for s is equal to goal, because from goal you cannot apply any action. You cannot sit at a goal, apply an action A. Sometimes people ask, does that mean obstacle? No, obstacle is not a valid state. It's not a part of the state space. So all states, when I say n states, I mean that there are n obstacle-free states excluding goal. Every state will have one equation like this, so there are n equations and there are n unknowns. So obvious thing that comes in mind is n equations, n variables. Solve it up. Any linear equation packet solver can solve that up, and you can get all the US. And once you get all the US, you can get all the pi s. And once you get all the pi s, this is exactly what I wanted to calculate. Simple enough, but then the equations are not linear. So equations are not linear. And once we cannot solve anything by a linear programming package, once we cannot solve anything by a simple technique, closed form solution, linear equations, what do? We make an iterative solutions. So we assume some value, we keep on improving it up. And that is exactly what I will do around over here. So what I'll do is, I will assume random US for all S, and I will say improve US, further improve US, and basically do this in a loop infinite amount of times. This algorithm is our first algorithm called as value iteration. And how will I improve utility of S? That's an interesting question. So let's try to exploit something in the equation. And these equations are basically extremely difficult because LHS has unknown terms and RHS has unknown terms. LHS has unknown terms and RHS has unknown terms. And in order to make it easier, let me write an equation where LHS of course has unknown terms, but RHS has known terms. So I write down exactly the same equation once more. I won't repeat explanation of it because it's a repeat of exactly the same equation. So the LHS is over here. And RHS is over here. So if you look at it, it's exactly the same equation except for I added a suffix so as to say that utility at the LHS is unknown because it's at the greater iteration of the algorithm, and utility of the RHS is at the previous time step and it is absolutely known. So it's exactly the same equation over here except for the LHS and RHS both have different variables. Now it's easy for me to say So assume random US for all valid S not equal to goal, and I say while forever. Now, if you want to say, or instead of while forever, so you say for t is equal to 1 to infinity. That's my algorithm. And now if you just want to break, so you just say if ut plus 1 s minus ut s submission for all s absolute value is less than delta or less than a small number epsilon, then break. So it's like the convergence would have happened where this explicitly is what is my error. Not in the classic sense. So this is basically the improvement as it has happened with time, and now with a lot of classes on supervised learning, you would know that how the error goes along with the improvement. So let me instead say that this is the improvement. Okay, now there are obviously, as algorithm, there's absolutely nothing to explain over here. It's same as a neural network learning. You start off with random weights and the weights keep on improving and improving and improving, and the moment they stop improving, so the gradient is small, the change is small, the improvement is small, you say break. Now, the interesting fact over here is the fact that number one, how can I say that the improvement is really improving it? For the neural network, you had this gradient thing, and because you had this gradient thing, you know it will keep on pushing towards the local optima. What happens around over here? Now, let me quote what is specific about this equation. So this equation has terms on the LHS and this equation has terms on the RHS on the same function. And this type of an equation is also called as the Bellman function. Bellman equation. And what really happens around over here is that an ideal solution has all US which satisfy this equation constraint. So you plug in all the available US over here and all the available US dash over here for all S dash. Okay, I am missing out on a summation for such a long time. My bad. I have no idea for how long have I explained without this summation. Had it been a class, somebody would have shouted out, what about a submission? I should be carrying in my hand-filled notes. Okay, so coming back, so you fill in all these equations and it followed exactly the same constraint. Now, what really happens in such iterated solution which improve with time, these equations are violated. So I say let these equations be violated to some degree, or I calculate by what degree are these equations violated. So if this equation is violated, the violation will basically be, so I say violation of Bellman constraint is just this minus this, so absolute value and let's say S dash plus gamma times U S dash. That's what's the a random equation. This is what constraint it will have. Now what I've done over here is, if you look at this equation, replace ut by this little thing. So for some variables, I'm making the Bellman constraint as 0. They'll exactly follow this equation constraint, and because I'm making that approximately 0, some variables are getting laden of a Bellman constraint. Next time, some other variables will get laden of Bellman constraint, and the Bellman constraints are the ones that will reduce along with time. And because of that, my actual error, not the improvement, which is a summation over all Bellman constraints over here. So the error is basically a submission over all Bellman constraints over here. That reduces with time. Once the Bellman constraints reduce with time, then I know my convergence is what is happening. In other words, when you just took in random values had nothing called as Bellman constraints. And by writing this Bellman equation, all that I have done is I have told something about the Bellman constraints, and because of that, my variables have now taken in new improved values. And because they've taken new improved values, the errors keep on reducing intuitively. So that's a simple algorithm which is called as the value iteration. You don't see learning rates over here because of the fact that, look at this equation, it has a nice closed form in terms of constraint solution, and it's not that I'm learning by some learning rate. The factors of learning rate are similar to supervised learning are by this discount factor. Now, something again interesting around over here is the fact that had supervised learning not happened, all you know is closed form solution. So given RHS, you calculate LHS, you know nothing that keeps on improving with time, constraints getting invoked, constraints getting resolved, and errors keep on reducing. Now, the value iteration unfortunately has too many continuous improvements until you converge to the best value which is possible. So that's what a value iteration would look like. So you slowly and converge until you get into the best value which is possible for every state US.